So thank you very much. Thank you very much for the invitation to participate in this very interesting conference and to speak. It's a great pleasure. So I'd like to talk about WKB. And this is, I think, what Professor Ekal calls Voros resurgence. So the plan of the talk is one, to talk about how to do the endless continuation. In some particular case. And then the second part, I'd like to talk about some more recent considerations to try to compute the exponent. And the second part is joint with Lyudmil and Kazarkov, Pranav Pandit. And then for the first part of this work was also with Alex Knoll. Then for kind of a subsequent part, which is not really related exactly to this question, but subsequent work in symplectic geometry with Fabian Hayden. Okay, so first the basic setup. So the basic setup is we have an equation. Let's start with an equation of the form, so I'll try to write this in a kind of standard form with an h bar. So h bar d plus or minus, let's say, plus a of z times a vector equals 0. Okay, so this is our basic ODE. And so it's singular in the variable h bar. So h bar going to 0. And we'll really think of this as a variable 1 over h bar going to infinity. Okay. So then, so let's diagonalize the matrix, okay? So and this is this is going to be the spectral curve. If we try to diagonalize the matrix, of course, we want to know what are the eigenvalues of the matrix. The eigenvalues of the matrix are multi-valued functions, and that forms the spectral covering of Z. So,
Carlos, what assumptions?
On A of Z, yeah.
well, some assumptions. Let's not be too specific. Let me make some assumptions. Let me first diagonalize, and then we'll make the assumptions later, okay?
In particular, is diagonalizable, yes? That's one assumption.
For example, yeah. We'll have a more specific problem in a minute. But, kind of the problem is that part of the discussion is going to not really exactly apply to this case, as you'll see. But anyway. Okay. So that means let's choose a matrix S of Z. Also, I'm being a little bit non-specific about what Z is. So Z is a one-dimensional complex. Z is a Riemann surface.
Compact?
No, I mean, not necessarily. I mean, if it was compact, we would really want to look at the universal cover anyway. So, roughly speaking, it's the disk. Okay. But there's this question, but I think which has already been evoked in previous talks. The question about the completeness of some kind of metric. Whether you sort of, and we're gonna somehow or other assume that you're not going to sort of fall off the edge of Z when you do your flows. Okay. So let's choose S of Z so that S inverse A, S is a diagonal matrix, which I'll for now write A1, AN. So let's just sort of, A is really the matrix of one form. So maybe when if I write the variable, then I'll have a dz, and if I don't write the variable, that includes the dz. Okay. So let's just look at an example. So I think it's important. I never really did this example precisely, but this is important to do this example, which is A is the matrix 0, 1, V of Z, 0 times dz. And then S, so S, the best thing to choose for S actually is v to the minus 1/4. Oh, sorry. V to the 1/4. No. I think it's minus 1/4. I think I made a mistake. There's a plus or minus maybe. And then S inverse, if I'm not mistaken, should be, but this might be mistaken. Something like, you can do the thing and tell me if I'm not. But anyway, and now, what is S inverse times ds? So S inverse A S, so the diagonal matrix is just what you think. So the V of Z, it's really the V of Z is really the coefficient of a quadratic differential, and it's V to the 1/2. The eigenvalues are V to the 1/2 and minus V to the 1/2. Okay, you guys all know this better than I do. But then S inverse, but maybe an interesting point here is S inverse ds. So when we make the gauge transformation, we get a term which is S inverse ds, which is kind of important. That, if I'm not mistaken, is like something like that. So the point here is that this has a logarithmic pole on the off-diagonal pieces, and we chose the 1/4 here so that it has 0 on the diagonal pieces. Okay, so now we get a new equation. Which is, so let's call the new A is just the diagonal matrix. Let's call this, R. This should be R. This is the rank. This is the rank bundle. And then B is this extra gauge term. Okay. And the new equation is D plus 1 over H bar times the A, the new A. Plus B equal times B. Okay, so this is the equation I actually want to look at. And then in the example, B actually has logarithmic poles. At the turning points. The turning points, well, in general, that's for the example, but the turning points in general are the points where AI minus AJ vanishes. Okay. Sorry. Now, what's the question? So the question is, so the question is, we fix 2 points in our Riemann surface. We fix a path from one point to the other. And let's let M, so M depends on H bar, is the transport matrix from P to Q. Okay, so this is going to have logarithmic growth. Something like that. So this has logarithmic growth, which is bounded by some constant in the size of 1 over H bar. The constant is basically the size of the matrix A along the path gamma. Okay. So this is, but this is an entire function of h bar, let's say. It's a function of 1 over h bar. I mean, I'm calling this h bar for obvious reasons here, but maybe the better parameter to think of is 1 over h bar, which I think some people are calling eta. Okay, so that's the question. So that's supposed to be a function. So that's the function in the non-Borel plane. That's the function which we're going to transform into the Borel plane. Okay. But before we do that, let me just write the expression for this function. So this is kind of important. Let me not derive this expression, but I'll let you guys imagine. So let's do it here. So M is going to be a sum of mi of h bar. So the sum is over I, the I are multi-indices I0, I1, In. This is N, not, this is different from R. So these are the matrix. These are the indices for matrix coefficients. Okay. And Mi equals, let's see. Let me write the formula, and then I'll write you the definition of the terms of the formula. Mi is the integral over delta n of e to the gi of z over h bar times b z. Okay. Now, what are the terms in this formula? So here, z means z1 up through zn. It's a point in capital Z to the n. Okay. So the terms in the formula. So gi is a function from capital Z to the n into C. So gi of z1 zn is the integral from the point P to Z1 of AI0 plus the integral from Z1 to Z2 of AI1 and so on. Okay. That's G.
So on the spectral curve, you should make universal cover or choose plus.
Yeah.
Or you follow your plus.
Yeah, okay, so, sorry, thank you. So we've kind of replaced Z by the cameral cover, actually, where the different diagonal terms are distinct. Yeah. So this is the Z new. So I should, well, right, I guess what I wanted to say here is really, sorry. This first order was to reduce to this case. So what I really want to look at is this equation where A, I really want to look at this equation where A is already diagonal. Okay. This example was to explain how, for example, in this typical quantum mechanics case, you can reduce to that case. But of course, you have to make the covering where you take the square root of V. But it's this, I mean, that's this. Remember, I mean, what I'm doing here is kind of limited in scope and so on. In the sense that I'm just fixing two specific points of Z and a path from one to the other. So that's going to be a little bit different from, for example, what happens if you try to use Foucault-Koundrov coordinates, where you need to choose flat sections that have a certain asymptotic property at singular points and that kind of thing.
It's just Laplace formula for the monodromy.
Something like that, yeah.
And excuse me, do you assume that the AIs are distinct?
Let's assume that the AIs are distinct, yeah. Assuming that, yeah. And in fact, maybe, it could have, well, okay. Let me not be too specific about the precise hypothesis here. Anyway, okay, yeah, but the AIs should be distinct, yeah. Sorry, and maybe the other hypothesis, which I didn't say, is that the BII are 0. We can assume that also by making a gauge transformation. That's kind of important. Okay. But again, that you can see that in the example. In the example, we had to choose the 1/4 there in order to get that property. Okay, anyway, so this is the function. So this is the main function which controls the exponential growth of our problem. Okay? And it's probably useful to notice that this is also equal to gi0 of p, maybe of q, let's say gin of q minus gi0 of p. So if we choose primitives gi of the AI, then we have something like that, plus a sum of gi k minus 1 ik of z k. Okay. So if you vary one of these points z1, for example, the variation of the function g there is given by the difference of the ai1 and the ai0.
Do your points lie on the same path, gamma? Or?
So for now, the points line, that's the next statement, which is the delta n is the set of points of the form gamma of t1, gamma of tn, where 0 less than or equal to t1 less than or equal to t2 and so on less than or equal to tn. So for the moment, the points are the z's are points on the path. Okay, and then what's b? So bi. So bi of z is really a form. So it's it's the form that you got by taking the matrix coefficients in an obvious way with these coefficients. So it's bi 0 I1 of z1 bz1. So B should be an n form, right? Because we're integrating over an n-dimensional real cycle. So this is n. So we're integrating over an n-dimensional real cycle in an n-dimensional complex space, and we're integrating a complex n form. Okay? So I think Maxime does this most often. Okay, that's all for the formula. Now, okay, let me, before going to the Borel plane, I think this is maybe important to say before we get to the Borel plane, because then we'll do the same thing in the Borel plane, but before we get to the Borel plane, the main point here is we would like to apply some kind of saddle point or steepest descent method for this integral. What does that basically mean? That basically means we want to move the cycle, because this integral is basically independent of the choice of cycle of integration, because it's an integral of a holomorphic form, which is closed. Okay? This is a holomorphic form, but we multiply by a holomorphic function, so it's still a holomorphic form, so it's still closed. So we can still move the cycle of integration. And we try to move the cycle of integration so as to minimize the real part of this function g. Okay? That's if we're trying to analytically continue in the plane, maybe I should draw that picture possibly.
H bar is real?
Sorry, I realized I should draw that picture now. So, so for the moment, 1 over h, let's see, so h bar is 1 over h bar is a complex parameter. So 1 over h bar is really any point of C. Okay? And the point is that this function, well, I guess we're not quite there, but yeah, yeah. So if we think of h bar as being real, and then we want to make the function as small as possible, then we're interested in the real part of that. Yeah, thank you.
So your H bar is real or complex now?
No, let's keep h bar complex, but in the example I was talking about with diminishing the real part of g, that's for the case of h bar real. If h bar had some other direction, then you would turn by that amount, and instead of the real part of g, you would diminish the real part of e to the I theta times g. Okay. So let's do the Borel transform. Okay. So now let's go to the Borel plane. So the variable c is going to be dual to the 1 over h bar parameter. Okay. So let's define m hat of c defined to be equal to the zero integral from, right, what I wanted to stress, but I said it already, is that this function has exponential growth of exponential order 1 of 1 over h bar. So we can make the following integral from 0 to infinity of e to the minus, I guess it's a minus, c over h bar times m of h bar times d of, so I'm sorry about this, but this is d of 1 over h bar. So I guess if we wanted to do dh bar, it'll be, there's a factor of h bar in there somewhere. As I said, I was really thinking in terms of the parameter 1 over h bar. Okay. And this is going to be a sum of terms, so we can also do the Borel transform of each of the terms in the sum. And if I'm not mistaken, the formula is the following, that the mi of c are the integral over the same cycle delta n of, there might be a sign problem, of bi divided by gi of z minus c, up to a plus or minus. Okay. I'm not sure, I don't remember if that was if there's a c minus gi or gi minus c. Basically, when you Borel transform this expression, you get that thing. When you plug that into here and Borel transform, you get that thing. Okay. So I guess this is probably a good place to point out that, so my whole investigation of this question was actually, I think in actual fact, has to be said, was strongly influenced by Professor École's work. Although I didn't necessarily really quite realize this at the time. But I was following Gérard Lemont's class as a graduate student, I was following his class on Fourier transform for L-adic sheaves. And, no, but yeah, okay, so it's not sure is laughing. But, you know, at the time, especially as graduate students, we became extremely adept at passing between the L-adic number theory kind of picture and the D-module complex geometry type of picture back and forth, basically. So, and also Lemont said, and somewhere in his course materials, he said, you know, one of the references for this course is École's theory. So, of course, this was a whole course about Fourier transform of L-adic sheaves. But then, when it came to have a problem in complex geometry, then it was natural to do a Borel transform and then try to look at the properties of the function in the Borel plane. Okay, so now let's see comments about this. So the first comment is that this path of integration depends on h bar. Okay, so sorry, depends on c. So this is well defined for absolute value of c bigger, let's say strictly bigger than this constant c2 that shows up here. And the path of integration from 0 to infinity is going to depend on the argument of c. So depending on whichever, if you have c which is big enough, then there's always going to exist a path of integration with the property that this is exponentially decreasing, okay, as 1 over h bar goes to infinity. Okay. but because of that estimate. So that's kind of the answer of this question about whether h bar is real or not. I mean, we have this function which is defined on the complement. So in the Borel plane, our function is defined on the complement of a disk. Okay. And then the inverse transform in this situation is that m of m of h bar is going to be the integral, a circular integral of maybe e to the xi over h bar times m hat of xi dxi up to a constant. And the circular integral to define m is taken around this region. So now, geometrically, what is this region? Geometrically, this region is obtained in the following way. It's just take the image. So let's say z dot is a sort of disjoint union of things of the form zi, where zi equals z to the n. Okay? And then we have just a function g from z dot into the complex plane, into the xi, and we should really think of this as the xi plane. Okay? And then we have this delta dot is sort of a sum of delta I. So we can just write this whole integral as a formal sum. It's just an integral over a single cycle. So we can write sort of m hat in a formal way. And m hat of xi is just the integral over delta dot of b divided by g minus xi.
Sorry, I didn't get it. This m hat should be a multivariate function, yeah? And you cannot choose its very big.
No, but that's in this case. So this is probably a slightly different case than some of the other resurgence properties that we're looking at. I mean, it's kind of the same, but we don't have like this infinite collection of poles on the real on the imaginary axis or something like that. In this case, this m hat of xi is a well-defined function, perfectly well-defined function on the complement of the disk of radius c2. Because just look at the definition. This m is an entire function of 1 over h bar. It's also defined at h bar at 1 over h bar equals 0, kind of trivially. Okay, m is an entire function, and it satisfies this growth hypothesis. So for any value of xi, we can choose the path of integration.
Can define maybe in half planes?
But you can those just glue together.
No.
They don't.
No.
Why not?
No.
We just defined the number this way.
It's not convergent. It's a real part. Half planes. It's only in half plane.
Yeah.
Yeah, but then if we choose a different half plane, we choose a different path of integration.
Yeah, and then you get cuts. Yeah.
Okay. But it's the same function.
No, but the picture which you draw, I mean, it's not on the half plane.
I mean, if you like, we can just write this formula.
No.
Why not?
But this contour integral is.
No, I don't agree. I mean, let's just write down this function. This function is perfectly well defined for any xi, which is what I wanted to say now. So this is well defined. So m hat of xi is defined if xi is not in the support of g lower, let's see, g lower star of delta dot. And this g lower star of delta dot is supported on a compact subset. All of these cycles have the property that g of the cycle is supported inside this disk. So if we take a value of xi which is not in this disk, then this integral is just well defined. And this function m of h bar is just equal to the path integral around this thing. I think the reason, so we were discussing in the train with Jean-Pierre, the reason why this is maybe a little bit confusing is because here we're not talking about irregular singularities. So if you introduce irregular singularities into the question, then the direction of the Stokes lines are going to depend on h bar. So you can't, so the irregular monodromy is not of this form just fixed to different points, right? The irregular monodromy is going to be an irregular monodromy in some Stokes directions, but which depend on the direction of h bar. That's maybe in Professor Ecol's talk was the combination of equational and co-equational resurgence. In this case, we're just talking about, for example, a compact Riemann surface. We don't have this irregular singularity question. So anyway, I mean, if you're convinced that there's a mistake, please let me know. But I don't think for our present purposes, I don't think that's. Okay, so now what are we going to do here? So now what's the goal here? So the goal is to, let's write this over here. I mean, so supposedly what we're going to do here should work in that type of case also, I suppose, but that's not what I'm claiming. Okay, so now what's the goal is to do an endless analytic continuation of this function, m hat of c. So what's the idea is that we just noticed that each mi has an endless continuation. So this is just sort of some slightly infinite version of Gauss-Manin. For a finite dimensional integral. Okay. So if this map G were a map of proper map of algebraic varieties, then this would automatically satisfy this property. And here we have a slightly infinite version because this integral is defined on this set Z, which is typically going to be like the abelian cover of a compact Riemann surface that you get by mapping it into its Jacobian. So there's some periodicity. But the singularities themselves are sort of, at least either contained in either finite points, or maybe in the worst case, if you have to blow up something or something, are just going to be compact subsets of Z to the n. So whatever happens around a given singular point is just like the algebraic geometry situation. So this kind of that's not really a proof exactly, but sort of in terms of general principles. And then, so the main question too is is that they converge. The sum of continuations converges. So let me just give the definition of endless continuation. Or weak endless continuation. So let's say fix a disk so let's fix a disk where our function is defined. And then it says that for any m, there exists a finite subset S index m inside the C plane, such that for any path we should start at a disk because our singular set might well have points inside that disk. So we can't just fix a single starting point. We need to fix a sort of infinite set of possible starting points. But we assume that our function is continued inside the disk already. Okay. So for any path starting in D0 and avoiding Sm of length less than or equal to m. So this is the property which I'm claiming we can prove here. I think it's probably useful to consider a weaker property. That's why I put the word weak here. I think it's probably useful to consider a weaker property because this is kind of a rather strong property, actually. So the weaker property would to require that the winding number of the path also be smaller than m. Then the statement is there exists a continuation along the path. If we don't put the winding number condition, then that actually tells us that you can go any number of times you want around a given singularity without sort of introducing new singularity. That doesn't seem like it would necessarily be true in general. Okay, so this is the definition I'd like to use for endless continuation. I think there might be other possible definitions. So that's the thing we'd like to prove here. And now, what's the technique? So to illustrate the technique, so the technique is that we need, so we can sort of make a general statement about one, but the point is that if we want to get the convergence, then in part one, we actually need a very specific continuation procedure. So
So what is rho here?
rho is a path. So any path in the C plane of length less than or equal to m, then, so
You can draw the picture.
yeah, so let me draw the picture. So let's draw a bigger version of that picture. So our function is a priori defined on the complement of this disk of radius c, okay? And we start out with our d0 here, okay? This says that if I choose a length like, the length of this blackboard, there's going to be a finite set of singularities, which could be outside of here also, such that if I continue along a path that goes like that, then I can continue my function along any path that goes around these singularities of length less than or equal to m. Then as m increases, the set of singularities gets bigger and bigger. That's this resurgence phenomenon. Okay? So now, what you might say is the first thing to do, of course, is to start from this point and sort of continue around the region and see which singularities you hit first. This property implies that there's a finite set of singularities that are hit before any other ones, and then the real domain, the real sort of complement of a convex domain on which m of psi is defined is going to be the convex hull of that finite set. Yeah? We're claiming any rank here. So, yeah. Okay, so the point here is to use a specific continuation procedure in order to get a control on the convergence so that we can treat the convergence question. And what's the procedure? The procedure is to use gradient flow. So now, in the talk, I would like to discuss the case where we're just, rather than trying to continue along some complicated path, we're just trying to move this domain of integration over to the left here, until it hits its first singularity, okay? That's kind of an easier question. But what I would just like to point out is that it's the same procedure works to continue along any sort of piecewise segmented path. We just apply this moving procedure along some neighborhood of that path, and then move in the opposite, and then move in this direction, and so on. That requires some, technical things that are not really very interesting. So let me just not discuss that here, but that you can do that. So let's just assume that we're just trying to decrease the real part of g. Okay. So if we're trying to decrease the real part of g, then we use the gradient flow of. So what we really want to use is the gradient flow of gij of the real part, gij.
Excuse me. The fact that the Riemann circuit is of infinite type is not a problem?
Well, so when you, so as I said, I wasn't saying really what hypotheses there are. You need to make a hypothesis that says that if you actually sort of flowed to the edge of the Riemann surface, that then you would have decreased the real part of g by an infinite amount. Okay. I mean, to do this process, we only have to decrease the real part of g by a finite amount, and even along our path of a fixed length, we only have to sort of decrease all the different real parts of the different rotations of g by a finite amount. So the kind of completeness properties that going to be that we would like to make sure that we don't get to the boundary of the Riemann surface before sort of an infinite amount of decrease. That's obviously a big problem in the case where B has poles, because in the case where B has poles, you really need to not hit the poles of B. So you need to draw a little circle around the poles of B, which causes exactly a problem of this sort. That's more complicated. I tried to discuss that in a preprint I wrote for Jean-Pierre's birthday celebration. It seems pretty incomprehensible to me, so I don't necessarily claim that it has to be without error and so on. The claim is you can actually even do that too. So that's why the claim says that even if B has, maybe let's say, well, I think any poles, this should still work, but that's a little bit more delicate. My original discussion of this was just in the case where B is holomorphic, but which unfortunately doesn't apply to the example. Okay, so the status of the proof. And the other statement, on that level is that in the case where B is holomorphic, you can get a better control over the type of the singularities that are met. In the case where B has poles, I don't have any idea how to control what type of singularities the function will have here. Okay. I think there's, sorry?
No longer convex.
No, just, the singularities at the singular points.
But these are periods or something.
No, the values of the singular points are periods. No, but the singularities of the function, the singularities of m hat at these points could have an essential singularity. So I think, it's definitely going to be a trans series. Maybe not convergent. You said probably not convergent in general. Particularly, I have to say I don't even know that there exists even one point where it's convergent. So that may be a caveat here. In the case where B is regular, you can at least show that the singularities have some kind of asymptotic expansion. So I'm hoping that in the case where B has logarithmic poles, I'm hoping that you would be able to show that it has at least 1 over C minus A0. I guess you guys call this A. I'm hoping you could show that the function has at least growth less than that, but that's conjectural for the moment.
Well, Steve, in the sense we have actually finite dimensional triples, not one dimensional. Yeah, it's more like almost a product. You get like simplex. Yeah. But
yeah, these are finite dimensional. Each term is a finite dimensional integral, so each term is pretty much controlled.
It's the sentence you do in product of copies of curves. Yeah.
Yeah. That's easy. So you might, that's easy. So 1 in principle is easy. 2, I won't be able to explain really why it's true anyway. But what I would like to just say is that in order to do 2 in a good way, you need to treat 1 in a systematic way rather than just by making a general statement like that, which is as follows. But it leads to something interesting. It leads to an interesting geometrical thing. So let's see how to do that. But so for now, what we would just like to know is that, as I said, I mean, rather than treating a general path, let's just treat analytic continuation in the plane like that, which corresponds to the case h bar real. Okay. So let's just try to push our cycle as much to the left as possible. And to push our cycle as much to the left as possible, we're basically just going to flow by the gradient flow of this function. So now let me just explain what the basic problem here. This is kind of the main phenomenon that's happening. I think I'm not going to get to the second part of the talk, unfortunately. Okay, so the main phenomenon is that this integral is that delta n, or delta I, which is delta n, is a relative homology class. It's a cycle with boundary. So remember, this is it's a real triangle in a real n-dimensional triangle in an n-dimensional complex space. This is z to the n. And so what are the singular points of delta? Delta should be on the board here now. Or did I just erased it? No. Delta is here. What are the singular points what are the boundary points of delta? Well, it's when t1 equals 0, or t2 equals t1, and so on, or tn equals 1. Or you can just see in this integral, the singular points are when z1 equals p, z1 equals z2, and so on up to zn equals q. So the singular divisor is z1 equals p union z1 equals z2. So it's a union of, I guess, n plus 1 divisors inside z to the n, so it's just a complex simplex. Okay. And this integral is going to be independent of the choice of representative. In here, in this relative thing. However, the gradient does not preserve the boundary. Okay. So what do we need to do? We need to descend the cycle. So we need to inductively inductively descend the cycle on the boundary first, and then descend the whole cycle. So let me just draw the picture, so I think this should become relatively clear with the drawing. But the point being that we want to do this in a systematic way, so we want to apply some actual flows to descend the cycle, because that's the only way we'll have a control over the size of the cycle as a function of n. Okay. So what happens if we do this for delta 2? Okay. I guess t2 is bigger than t1, so something like this. Okay. So delta 2 is a cycle like that. So if we draw this inside z2, if I'm not mistaken with my direction here. Yeah, that's good. So this is Z1 equals Z2. This is Z2 equals Q, and this is Z1 equals P, okay? So these are complex planes, right? Or these are complex, Riemann surfaces. So this is Z2, and this is Z. Each of these things here, each of these guys is a Zn minus 1. And they intersect in Zn minus 2s and so on, okay? So what happens so what do we need to do to descend? So if we apply the gradient flow on this triangle only, then it's no longer going to be have the boundary on the boundary. Okay. Of course, that gradient flow is a part of the picture, but we should first apply the gradient flow to the path on the boundary, like that. Yeah. Then do that on each boundary piece. So one thing to notice is that the boundary pieces have their own indexation. If this is a Zi, this is going to be like a Zi prime and so on. The functions g are compatible. So the function g on the z with its indexation on the boundary is compatible with the other one, okay? So we apply the gradient flow on the boundary, and then we take the triangle plus the homotopies on each of the boundary pieces. I mean, this is the flowed path. So this is might have hit a saddle point here, for example, typically. Yeah. So this is a flowed down path here. But we have to take the full homotopy of this path, and then add that to the triangle, and now we can flow this entire piece down. Okay. Now the new cycle. What's the new cycle? So this part here is on the boundary, right? So we can use this as a new boundary rather than this one. Okay. So the new cycle is going to be everything obtained by applying the flow plus what was obtained by applying the flow to the boundary pieces. Okay. So it's going to be sort of the bottom of this picture plus the side. Okay.
Excuse me, I don't understand why the vertices are separated by the
Different
gradient flows.
I should go to the same direction.
Because the g function on this thing is different from the.
No, vertex of a triangle.
But here we're flowing by a gradient flow, which does something to the points P and Q also. But of course, it means that the flowed path of this boundary is this plus this plus this. I'm doing the two-dimensional case. This picture is the one-dimensional case of what I'm trying to say here in the two-dimensional case. There's the flowed down part. From here, we flow down this segment. That gives us this segment. But we need to add this piece and this piece, which are given by the flows of the boundaries. So the same principle in 2 dimensions is going to tell us that the full cycle we want is the flow down cycle of this stuff plus the boundary pieces. Okay. Now the point is that the resulting cycle.
So is that my gradient flow of the given function is always I should take into account the previous boundary, which I should start with now?
Yeah, that's basically the idea. Yeah.
But what do you do with the vertices?
The new boundary of the cycle is this. So it still goes through the vertices.
Okay, but then you write the new ones on the boundary.
No, the vertices of the new triangle are still the same as the vertices of the old triangle.
Okay.
But we had to flow. So what happens if you think about this, maybe this is hard in 2 minutes, but if you think about this for a little while, if you've got a bunch of different flows, and I think Misha even wrote a paper about this. If you have a bunch of different flows, you can actually get the following structure, which is you have a sum over labeled trees of a sort of a cycle, let's call it delta for the tree, t or something like that. What's delta for the tree? So let me just draw this like this. So this is our original path gamma. And then okay. So in this picture, there's a piece which corresponds to the original triangle. That's going to be the tree, these two trees. That's going to be trees like that. Okay, so with a 1. So this is the segment 0, 1. Okay, the top thing of the picture is the segment 0, 1. The places where these attach, those are, you might say, the places in the original cycle delta, which are at the origin of the point. Okay, so if we take our original triangle and flow down, we get the picture T1, T2, 1, 1. Okay, but we have some other pictures which are, for example, just T1. Now I'm probably going to have a mistake here, but there's several different possibilities. We need a label here. So there's going to be like a S11, or there's going to be a 1S, for example. There are several different parts of the picture which correspond to this, to a point here, right? The point here we got flowed, I guess. So here we flowed down by the gradient flow of, flowed down all the way by this gradient flow. I guess the point is that, kind of a detail here is we don't really want to do the gradient flow inside the Z2. We really want to do first a gradient flow in one direction and then the gradient flow in the other direction. So those are going to be either the 1S or the S1 cases. So there's maybe two segments, I mean, maybe probably S0. There's going to be really two segments of this picture. Okay. And the picture on labeled trees is we have a tree labeled with 0, 1, or some variable s, and we have the top edges are labeled T1 up through Tk. Okay. And so there's going to be variables S1 up through Sn minus k. The variable is T1 up through Tk. Okay. And the image of this, so this diagram is labeled by the, now in the regions of the diagram we have the indices. And so on. And the image point corresponding to this diagram is obtained as follows, which is you flow along the gradient flow for the function g. You follow along the gradient flow for the function real part of g, I, k, I, l for the time designated by the variable. Okay. Now, what are the critical points? I should probably finish here. What are the critical points? The critical points are the case where you end on all the different critical points. So the critical points of this whole picture are the case where the bottom of the tree, these are all the different critical points. Okay? And so if you think about it, this is exactly the picture of spectral networks. So these gradient flows. So to be more precise, it's really spectral networks, but not for an imaginary direction, but for a real direction. And the real direction you could actually choose, because in here you could either flow this way or that way. It doesn't really make a difference if you're trying to move to the left. Okay.
So just a question, how do you connect the whole structure with that you say that each leaf corresponds to a critical point?
Right. So it's one. What are the places where you can't flow any further? The places where you can't flow any further are when you've hit a critical point in all the different variables. If you hit a critical point in some of the variables but not the other ones, then you can keep flowing in the other variables. So the places where you can't flow any further, so these are going to generate the thimbles, are the places where you have critical points on all the bottom vertices of the tree, basically. So it says that the locations of these critical points are things obtained by by doing the gradient flow down to a critical point along each of these edges of the tree, basically. That's essentially some kind of spectral network type of picture. Let me just finish by a caveat, which is that in the case that we were discussing before, the more advanced case where the B has maybe first order poles at the turning points, then what I don't know how to control with this procedure is the fact that any variable is supposed to stop at a turning point. So this point here might be a turning point, but for a different variable, not necessarily the I0, I1 variable. So that's different from Gauss-Mornitsky. So a priori, from this procedure in any case, the locations of the poles, you have to add extra possible locations of the poles, basically. And that's why I wanted to say in part 2, which is that maybe there's some hope using our work with Ludmila and Panov on harmonic maps to buildings. Maybe there's some hope, at least in the case of SL3, of getting a more precise information on the location of at least the first pole, basically. Namely, I think the conjecture is that the location is going to be this type of picture, but where this is the I0, I1 turning point, and so on. Okay. I guess I should stop here. Let me just comment. Why would you want to prove that? How would you want to prove that this converges? Well, basically, when we do this flow, we're always decreasing the real part of the function. Okay, and then we're going to cut off our cycles when we've decreased that by a finite amount. So the size of the cycles is going to have some kind of condition like the sum of Si less than or equal to some constant. And this generates an exponentially small region, in fact. Together with the fact, of course, obviously the original delta is exponentially small. Factorially small. This generates a factorially small size. And in the original cycle has a factorially small size. Okay. So rough, and then the calculation is that sort of the number, you have to calculate that the number of cells you get here is some constant to the n. So constant at the n divided by n factorial converges. That's kind of the very rough. So I'll stop.
Questions or comments?
Question. In the spectral network, this is still open with the equation, exponential bound, yeah? Does it appear in... So
what's the, on the number of spectral networks?
Yeah, but maybe there are more complicated things because we have just trees, yeah?
No, but, so, okay, and this gives us slightly more precise information, which is that it's only the spectral networks that you get by this procedure. So it means that they have to go up and then cut the path. So I think that there's only finitely many.
So you don't have closed cycles.
Yeah, it's good. Okay.
Well, for a given path, and we're fixing the P and the Q and so on, then the number of spectral networks that are going to cut through the path in that way is finite.
It seems to me that this aspect of the theory which you have covered should go over to higher dimension. And I especially think of the Balian block formalism, which I briefly flashed on, which is a system of integral recursion with integrals exactly like the one on the top there, with denominators. And so this would be very nice if you can prove, because Balian block is formal, if you can use to prove resurgence in higher dimension.
Yeah, maybe. That would certainly be fun to do. Let me just comment maybe that, as far as I know, but maybe, I guess you probably know better, but from just kind of a very a priori perspective, we're really using the fact here that you have a closed form formula for the function we're trying to compute. So we're not, so this is kind of not going in the same direction as what you guys are proposing, which would be fantastic, which is to take the perturbative series and sort of create the resurgent function. Here we sort of already know what the function is. We want to maybe prove some additional properties like continuation.
No, but your expansion is very similar to what Balian block wrote in terms of iterated integrations.
Yeah, okay, well, maybe.
But of course, there's a lot of rigorous work to.
But are they finite dimensional integrals?
Yes.
Okay. Okay, okay.
Spectral networks in higher dimensions.
Well, maybe, I mean, yeah. I mean, the initial idea is just to use some kind of gradient flow to find the critical points, basically.
So in the rank 2 case, the quantum resurgence WKB case, you recover the location of the singularities as found by Ekal, Pham, Donabar, and I mean the location of singularities is okay, but what about the nature of the singularities? How come that in your formalism you don't reach the nature of the singularities? Because they have very precise predictions for that.
Well, so in the general case, so in the this is kind of related to each term mi c. I mean, if you look at this integral, what are the singularities? If bi has logarithmic singularities, then we have we're going to have some kind of integral like, maybe Maxime can do this on top of his head, right? Something like dz1 up through dzn divided by something like z1 up through zn, but then times some kind of summation of zi minus xi. I think the integral may be something like that. So I think you can show that this integral has 1 over, norm of xi type of a behavior. But I was just doing that this week, actually. I was trying to think. But that's going to be the same. We're going to have this type of behavior for any value of n. So what that really means is that each mi is going to have a series expansion, perhaps, at the singularity points. But the series expansions all have the same order of initial term. So when you make the sum, the series expansion, if it existed, the coefficients of the series expansion in the sum will themselves be series in the coefficients of each of the coefficients here, which is different from, and that's like one of the main simplifications in the original case where b is regular. In the case where b is regular, the powers of xi that happen in the series expansion go up. So any given coefficient is just a finite sum. As far as I can tell, you also have powers of logs in those series that also go up. So the sum is not going to be a regular thing. It's going to be a trans series with higher, it's going to have higher powers. It's going to be like sum of xi to the n times log xi to the m, something like that. But where m, the value of m goes up as a function of n, at least. That's in the regular case. In the irregular, sorry, that's in the case, don't mean regular, the case where b is holomorphic. In the case where b has poles, I don't even see why, the powers of log could all happen at the first term, as far as I can tell. Maybe I'm missing something, but.